In this set of class notes, we're going to do a couple of things. The first thing is we're going to do two examples that are kind of rehashes of what you might have looked at in the video notes, but they're opportunities for you to kind of put yourself to the test. So pause the video, do examples 1 and 2, see how you do on them, and then after that we're going to introduce some new material. So we're going to specifically look at how logarithms can be used in some specific applications. All right, so hopefully you've had a chance to try both examples 1 and 2. So let's take a look at these. All right, so we have this population that is decreasing. It had 29,000 people in 2006. It currently has 25,000 people. And we want a function that gives the population as a function of the years since 2006. And I can already see I have a typo here. This should say decreasing, not growing. Clearly we're decreasing. So we're assuming that the population is decreasing at a constant continuous decay rate. All right, so let's go about creating this function. Now when they say continuous, right, I think it's nice to be thinking about this type of a function, right, where I have the population as a function of time is this initial value times e to the rt. Now remember, t is years since 2006, right? So it's always nice to just kind of note what t equals 0 actually means, right? T equals 0 is 2006. All right. Now let's see if we can construct this function here. So it said it had 29,000 people in 2006. Well, that's going to be then our initial value, right? That's going to be our P0. So we know for sure we can just put 29,000 in here. All right, and then it says it currently has 25,000 people. Okay, so currently, what does t equal? Well, if 0 is 2006, then currently t equals 14, right? So 14 years later, we're in 2020. So t equals 14, and p of 14 we know is 25,000, like they told us in the problem. So we can plug 25,000 in for the population. And that's going to be the case when I can plug 14 in for t. So our only unknown is r, and so this is what's going to allow us to have the function that's being requested of us. So of course we can start by getting the exponential part by itself. And we can do some nice canceling here, right? Divide by 1,000 on top and bottom of that. So we end up with 25 29ths is equal to e to the 14r. But of course, if we take the natural log of both sides, we know that the e is just going to go away, right? So it's the natural log of 25 over 29 equals 14r. And so dividing by 14 finishes solving for r for us. So that all leads to this, that the function is 29,000 e to the natural log of 25 over 29 divided by 14 times t. So there's our function right there. Now the interesting thing here is, this is an exponential decay function, right? And when we have an exponential decay function, what we're expecting is a negative in the exponent. But the thing to remember is that anytime you take the log of a number smaller than 1, you do get a negative number. So we are in fact getting that property that we expect because that is negative. All right, so let's take look at example 2, and if you didn't do so already, I really encourage you to pause and try this one on your own before we discuss it together here. All right, so there's our function. And so unfortunately, this function's a little too timely for my liking. So this is an outbreak, in this case, just plain old influenza in a particular region, and it's keeping track of the number of people who have become ill with influenza, and T is measured in weeks. So in part A, it asks us, how many people became ill with the flu when the epidemic began? Okay, well, when the epidemic began, that means no weeks have gone by, right? So that is just me plugging in 0. Now, a lot of times we can take shortcuts when we plug 0 in for our independent variable, but in a function as complicated as this, we do just need to go through the work of seeing what actually happens when 0 gets placed in there for t. So if I have 5,000, sorry, there should be an e right there, right? 5,000 e to the 0, that's just 5,000 times 1, right? So we would have 100,000 over 5,001, which is basically 20 people. So when they started keeping track of this, we've got 20 people infected. So part B asks us how many people were ill by the end of the 4th week. So of course there, our job is just to plug 4 in for our t value. Now the thing that's definitely worth saying about this is that I think that it makes a lot of sense, since e to the negative 4 is not going to be a nice number, just to type this in your calculator as is. But please remember that you got to be careful about how you use your parentheses. So when you go to type this in, 100,000 divided by, you can't just type in 1 plus 5,000 here. You got to type in parentheses 1 plus 5,000 and then e to the negative 4. Right, because you want to divide 100,000 by all of this, not just the first number that you put there. And so about 1,080 people is what we get. So then part C asks, how long did it take for 12,000 people to become ill? So this time they're telling us how many people are ill. They're asking us, when does that happen? So we can put 12,000 in for the function value, but we don't know what t is, right? So we want to solve for t. Now, of course, in situations like this, right, we know we want to get this out of the variable out of the denominator, right? So we can always multiply by that denominator as long as we do it on both sides. So go ahead and do that. And so we get that nice cancellation over there on the right side. And then our whole goal is to get that t isolated there, right? So we're going to distribute this to both terms. So 12,000, get that t untrapped from inside the parentheses. And then 12,000 times 5,000, that's going to end up being 60 million. So let's go ahead and do that. So 60 followed by that many zeros is equal to 100,000. And I forgot my e to the negative t, sorry. That's pretty important there, isn't it? And then, of course, we can start to get that e to the negative t by itself. So 60 million e to the negative t is equal to 88,000. And then, of course, we can divide by 60 million. To get e to the negative t all by itself here. And so we can do some simplifying that's definitely worth doing, right? Divide by 1,000. Then we could also divide top and bottom by 8. So 11 on top. And let's see, on bottom here, when you divide 60,000 by 8, you're going to get 7,500. So we have 11 over 7,500. So let's clean this up a little bit. So e to the negative t is equal to 11 over 7,500. But then from here, we know how to deal with this, right? We can take the natural log of both sides. So we end up with negative t is equal to the natural log of 11 over 7,500. And right, remember, this is a negative number, right? It's a number. You're taking the log of something smaller than 1. And so it's definitely negative. And so that's equal to negative t. So of course, t is going to be equal to the negative of that. And when you punch that in your calculator, what you get is about 6.5. So that means that it's going to be about 6.5 weeks, 6.5 weeks, when we get 12,000 people who are ill. And then this very last question here says, in the long run, about how many people will became ill due to this epidemic. Well, the key here is that in the long run means what happens when time goes on, right? As t gets big. So this is where we want to do one of those analyses where we say, as t gets, and it doesn't really need to go to infinity to start to see this, but as t gets large, f of t, well, first of all, that equals 100,000, right? Over 1 plus 5,000 e to the negative t, right? But to think about what happens when t gets large, a lot of times it's nice not to have a negative there, so we can always put it in the denominator of the fraction so that we can make better sense of it. So of course, if t gets large, then e to the t gets large. And so this term here is going to 0. And so that means that this function must be going to 100,000. So as time goes on, the idea is that the epidemic is approaching 100,000 infections in this particular region. All right, so now we're going to move on to some new material here. We're going to start by talking about some applications of logarithms, and we're going to talk about logarithmic scales to start with. So a logarithmic scale is a way to demonstrate the relative position of numbers. In this case, we're going to use the example of planets in such a way that it makes things that are far apart not have to be so far apart when you use this type of a scale. Okay, so if we look at this first diagram here, this is showing us the positions of the 8 planets in the solar system in millions of kilometers from the sun. Now, if you know anything about our solar system, you know that the rocky planets are all squished into this very small space very near the sun. And then the gas giants are really spread out here. So when you look at the solar system in this way, in terms of just the absolute distances from the sun, it's really hard to get a sense of, Mercury, Venus, Earth, and Mars's uh, position relative to each other because they're just crammed on this little tiny chunk of this number line. But a logarithmic scale can make it look like this down here. Now, what a logarithmic scale is it's literally going to be the log of the distance. So we're going to chart the log of the distance as opposed to the actual distance. And so we'll move down here. And so when you see on a log scale the number 2, what that means is that the actual distance is 10 to the second power. Okay, so why is that? Well, if I go up here and find Venus, so the distance from the sun to Venus is about 108 million kilometers. Okay, so if you take the log of 108, okay, I think we could all agree that that's pretty close to the log of 100, right? So what does this mean, right? The log base 10 of 100, what are we saying? We're saying, what do I take 10 raised to in order to make the number 100? Well, I would take it raised to the number 2, right? So that is why you see Venus really close to the number 2 on the log scale. All right, so let's look at an example here. So example 3 says that although Pluto has lost its planet status, we're going to locate Pluto on both of the number lines above. So it is approximately 5,906 millions of kilometers from the sun. Okay, so here we go. And I guess that would be 5.9 billion kilometers from the sun would be another way to say that. All right, so let's first go up on just the regular number line here, right? Notice we're going every 2 notches represents 500 million kilometers. So here we go. So this would be 5,000, 6,000. So that means Pluto would put itself somewhere right up here. Okay. All right, but what about on the log scale? All right, well, first of all, let's just say this. If we want to do this without a calculator, well, all we have to do is find the nearest powers of 10. So what we know is that 5,906 is between 1,000 and 10,000, right? So what that means then is that the log of 5,906 is somewhere between the log of 10,000 and the log of 1,000. But of course, the log of 1,000, log of 10,000, right, is just what do I take 10 raised to make this number? Well, in this case, it's 3. Right? And then here it's 4. It's just the number of zeros. So we know that it's going to be somewhere between 3 and 4, right? Now we know it's bigger than Neptune, so it's got to be up here, but we know it's smaller than 4 for sure. Okay, but then what is it actually? Right? If we go ahead and put it in our calculator, there's nothing wrong with that. We get 3.77. So 3.77, let's look carefully at what this is. So 3.75, so 3.77 is maybe like right there. So there's where Pluto is going to go on our log scale. So log scales are actually used quite a bit in a lot of different contexts. So this is just one simple example of a log scale. But if you're going to go on into a number of the sciences, you're going to actually use this. All right, the one other application I want to show is something that you or at least have a passing familiarity with if you just like watch the news after an earthquake, and that is the idea of the magnitude of an earthquake. All right, so you hear things like the earthquake was a magnitude of 6.2 or a magnitude of 7. Okay, so where does that come from? Well, magnitude is a scale that's based on logarithms. All right, so the way you do it is you take 2/3 times the log, the common log, of this S, which we refer to as the seismic moment. Just think of it, it's a measure of the energy output of that earthquake, divided by S0. Now, S0 is like kind of this baseline measure for the seismic moment. And you can use the number 10 to the 16th if you want. In a lot of problems, it's not necessarily, you don't necessarily need to use that specific number, but that's what it is. All right, so in example 4, it asks how many times greater is a 7.1 magnitude earthquake than a 6.1 magnitude earthquake, and I should say in energy output. Could be a little more complete there. Okay, how many times greater is a 7.1 than a 6.1 magnitude earthquake? So what we're going to do here is I'm going to talk about this S. This S is that energy output, right? How powerful it is. So what we're going to look at is really how many times greater is, I'm going to do this, S, and I'm going to put a little 7.1 next to it, than S with a little 6.1 next to it. Okay, so the seismic moment for a 7.1 magnitude earthquake versus the seismic moment for a 6.1 magnitude earthquake. All right, so when you talk about how many times greater is one thing than another, that should involve division, right? Or in other words, how many times does this one fit into this one? So the strategy here should be, let's take S 7.1 divided by S 6.1. Okay, but the problem is we don't know either of those. Okay, however, what we do know is we do know the magnitude associated with each of these seismic moments, right? So on the one hand, I know that 7.1 should be equal to 2/3 times the log of the seismic moment for 7.1 over this S0, which is 10 to the 16th. Okay, but what I can do is I can solve, let's do that, let's solve for this. Okay, I can do that because I can, first of all, multiply by 3/2 on each side. So when I multiply by 3/2 on each side, what I end up with is 10.65 on the left is equal to, and it's the log, and remember it's base 10 if it's not written there, of S of 7.1 over S0. But if I have that, I can now rewrite that in exponential form, right? So I can say 10 to the 10.65 equals the seismic moment for 7.1 over S0. And then to finish solving for this, we can just put S0 on this side. Okay, so we've just isolated this. So I can put S0, 10 to the 10.65 here on top. I can do the same exact thing with 6.1. So let's do that down here. Do it another color so it's a little easier to follow. So 6.1 is equal to 2/3 log of that, multiply by 3/2 on both sides. So this one gives me 9.15 is the log base 10 of S6.1 over S0, which is 10 to the 9.15. So I've solved now for the 6.1 magnitude earthquake seismic moment. So then I can plug that in right there. And so you can see why I don't really need to bother putting that number in for S0, because it just ends up canceling out. And then we know how to deal with division of like bases. We just end up subtracting, right? So 10.65 minus 9.15. So that's going to be 10 to the 1.5. And when you put that in your calculator, you get about 31.6 times greater. Now, depending upon how much attention you've ever paid to news reports about an earthquake, you may have noticed that they'll talk about an earthquake being 7.1 or 7.2 magnitude, and whatever country it happens in, especially if it's got infrastructure that's not really built to withstand earthquakes, it can be quite devastating. And then you talk about a magnitude 6 earthquake, and especially in a developed country where you've got building codes that plan for earthquake proof, and it doesn't seem to do anything. Well, you can kind of see what's happening now. It's 31.6 times greater by going up on the magnitude scale just by 1, from 6.1 to 7.1. So you can see why there's such a difference there. All right, so in this last example, it says if a particular earthquake is 58 times as intense as a 5.7 magnitude quake, what is the magnitude of the larger quake? All right, so what we know is that we've got this 5.7 magnitude quake, and if we take 2/3 times the log of its seismic moment, which I'll just put as S with a little 5.7 next to it, over S0, I know that that's going to give me 5.7. Okay, but we're talking about an earthquake 58 times as intense as a 5.7 magnitude earthquake, and we want to know its magnitude. Well, if we want to know its magnitude, we should take 2/3 times the log of its seismic moment over S0. Oops, sorry. Okay, but what is its seismic moment? Well, we know that it's, whatever it is, it's 58 times the other earthquakes, right? So I can just say 58 times that. Now, if you notice, this and this look very similar. The only thing that's different is this multiplying by 58. Okay, but let's also keep in mind that we have some log rules that we can use. So if I put a 58 here, and then I separate it out from this part that's familiar to what we had before, I know there's a log rule that says I can turn this into an addition problem. So keeping the 2/3 out front, I'm just going to, 2/3 times what I'm going to do to this expression is going to be log 58 plus log S5.7 over S0. Then if I put my 2/3 back through to both of these terms, I get 2/3 log 58 That's something I can type in my calculator. Plus 2/3 log of S5.7 over S0, which I can't type in my calculator, but guess what? I already know that that's equal to 5.7. So punching that in the calculator and adding 5.7 to that gets me 6.88. So if I have an earthquake that is 58 times as intense as a 5.7 magnitude quake, then the magnitude of my larger quake has to be 6.88.